Okay, more centripetal force examples. In number 1, we have a car, mass 1,800 kilograms, traveling at 15 meters per second around a 35 meter radius curve. The coefficient of friction is 1. Will the car successfully round the curve? Okay, well first let's make a data table. We are given the mass, the speed, the radius of the curve, and the coefficient of friction. Now, for the car to round the curve, which is part of a circle, a centripetal force is required. Okay, now centripetal forces must always be provided by other types of forces, and in this case, the force that will be providing the centripetal force is friction. Okay? Alright, so the question becomes, is there enough friction in this case? Alright. Well, first, let's find the centripetal force needed to get around the curve. Okay, now, given this data from our two choices for centripetal force formula, let's use this one, mv squared over r. Okay, we'll plug in our data and get our calculators. So pause this at this time and get an answer on your calculator. Hopefully your calculator said 11,571 newtons. That's the amount of centripetal force the car needs. Okay? Alright, now let's find out how much friction force is present. And we can use our friction formula. Force friction is mu times the normal force. Remember, the normal force is the same as the weight. And the weight is equal to m times g. So, I'm going to substitute mg in for the normal force. Alright. Insert my numbers. Okay. And again, pause and pick up your calculator. And hopefully your calculator said 17,640 newtons. Alright, so here's what we have. We have a force of friction, 17,640 newtons, and centripetal force needed, 11,571 newtons. Notice that the force of friction is greater than the centripetal force. So, ask yourself, or talk it over with somebody sitting near you, is there enough friction? Will the car stay on the road? And the answer is yes, there's more than enough friction force to provide the necessary centripetal force for the car to round the curve, so the car gets around the curve. As a matter of fact, the car could even be going a little faster and still make it, because if the car is going faster, there will be more centripetal force needed, but again, there's lots more of this than there's this. So the car could go faster and still make it around the curve. Of course, there is an upper limit, okay? And there will be a point where the car is going so fast that the centripetal force needed will exceed the amount of friction force present. Okay, so there is a maximum speed. And this next example addresses that. A motorcycle and rider have a combined mass, okay, and wish to get around this curve. If the coefficient of friction is this, what is the maximum speed the motorcycle can go and still get around that curve? Okay? Well, centripetal force, again, is provided by the friction force. Okay? Let's find out how much friction there is in this case. The friction force formula, mu times the normal force, which is equal to mu times the weight, mu times m times g. Inserting our numbers. Okay? Pause, pick up your calculator. And my calculator said 3,136 newtons. This is the amount of friction that's there, and so this is the amount that's available for the centripetal force. Right at the limit of the maximum speed, every newton of friction force is going to be used for centripetal force. So I'm going to set centripetal force equal to the amount of friction that's there. Okay. Now, what we want to solve for is v. So we're going to use mv squared over r, and we're going to solve this for v. Okay? Now, first of all, let's multiply by r. And we get cancel, cancel. And this, turn it around. mv squared is equal to r times the force. Okay, I want v, so I'm going to divide out the m. And we get that v squared is equal to rf over m, which we will now square root to get this. Okay? Inserting our numbers. Pause, pick up your calculator, and the answer is 14 meters per second. So the motorcycle and rider can go 14 meters per second. That's the maximum speed that the vehicle can go, and still successfully negotiate that curve. Okay. Now, as it turns out, this speed is the same for whether it's a motorcycle or a car or a dump truck. This is mass independent. Okay, and the next example shows that. Show that the maximum speed to get around the curve is independent of mass. A dump truck has the same maximum speed as a motorcycle, assuming, of course, that the coefficient of friction is the same for both vehicles. Okay, we have to assume that, and it's approximately the same. Okay, for any type of vehicle. Kind of depends on the tires, and the tires are made of pretty close to the same compound. Okay. Anyway, so let's show this now. To do this, what we're going to do is we're going to set the centripetal force equal to the friction force. Okay? Every bit of friction there is going to be used for centripetal force at the maximum speed. Okay? Now, centripetal force, yeah. All right, now centripetal force is equal to mv squared over r, and friction force is equal to mu times m times g. Notice that there's a mass on both sides that we can actually cancel out. Okay? So interestingly, the mass term goes away. Now if you actually consult example number 2, you'll find that to find the friction force, we multiplied by the mass, and then to find the speed, we divided by the mass. So one time we multiplied by it, another time we divided by it, so it canceled itself right out. So it doesn't depend on it. Okay? V squared over r is just mu times g. Okay? You might not have expected that, but it's true. Now, multiplying by r, because we want to solve for v, right? Multiplying by r, we get this, and then we get this. Okay? And this is the maximum speed to negotiate a curve of radius r given the coefficient of friction mu. Okay, you can put this in your equation bank. You know, label it well because it's a special case formula. All right, and it's mass independent, which is interesting. Okay. All right, now we're going to apply this to example number 2, our motorcycle example. That was the mass, that was the radius of the curve, that was the coefficient of friction. Okay, so this is the maximum speed to get around. All right, and we can plug our numbers in, and I invite you to pause, crank this thing out, and you'll get 14 meters per second, just like before. Okay. Okay, one more example. A box is on the bed of a flatbed truck. It is unsecured. Coefficient of friction is 0.3. Truck turns a corner of radius 40 meters at speed of 25 miles per hour. Does the box stay on the truck or does it fly off? Okay. Okay, here's my data. All right. Now, let's find out how fast the truck can go and still have the box stay on. Let's find the maximum speed. Of course, the box is going to be going that speed too, right? So how fast can the box be going and still negotiate that curve? Because if you consider only the box, it's going to travel around the curve also, right? Hopefully, anyway. So let's find the maximum speed. Okay. Pause. Crank it out. My calculator said 10.8 meters per second. All right, so this is the maximum speed that the truck and box can have and still have the box remain on the truck. Okay. Now the question becomes, is this greater or less than 25 miles per hour? Okay. Right. Now, you might think, well, 10.8 is less than 25, yeah, but we have to consider the units too. I mean, the units are not the same. So right now we're comparing apples to oranges, you know. We need to compare apples to apples. Okay, so what I need to do is I need to convert one of these units to the other. All right? It doesn't really matter which one, but I'm going to convert miles per hour to meters per second. Okay? Now, we did conversions early on. Okay, you remember how to do that? We set up this bracket system. We need a conversion factor, and I looked it up. You can look it up too. There's a conversion factor. I didn't have this memorized, just looked it up. And I want to convert miles per hour to meters per second. Okay, I got miles per hour, I got meters per second. I want to cancel out miles per hour. Where do I put miles per hour so that it cancels itself out? And yeah, in the denominator, right? So I put miles per hour in the denominator. Meters per second is then in the numerator. That's the only place for it to go. And then these cancel themselves out. Okay. And then when you operate your calculator, you'll come up with an answer of 11.2 meters per second. All right. So the truck and the box are moving at 11.2 meters per second. From the previous calculation on the previous slide, the maximum speed for the box to stay on the truck is 10.8. Oh dear. Notice that they're moving at 11.2, but the maximum speed to stay on is 10.8. So unfortunately, the box slides off the truck. They should have tied it down. Okay. So there you have it. When cars are going around curves and other stuff going around curves, friction provides the centripetal force needed to negotiate the circular track.